All timelines are happening now, not sequentially, not in some cosmic queue where one history plays out, ends, and then another begins. Simultaneously. Right now, as you read these words, there is a version of you making a different choice. A version of you who picked up a different book, who stayed home instead of going out last Tuesday, who said yes instead of no, who turned left instead of right. There is a version of you who never encountered this video, and a version of you who encountered it and stopped watching after 30 seconds, and a version of you who is watching it for the second time. All of these versions are equally real. All of them are happening right now. In branches of reality that split off from shared histories, that are no longer in contact with each other, that cannot communicate or interact, but that exist with the same physical reality as this branch, this moment, this you. This is the many worlds interpretation of quantum mechanics. And it is not, I want to be very clear about this, a fringe idea dreamed up by someone who had too much coffee and too little sleep. It is a serious, mathematically rigorous, increasingly mainstream position in the foundations of physics. It was proposed in 1957 by Hugh Everett III, a brilliant graduate student at Princeton. In his doctoral thesis, it was largely ignored for decades. And then something happened. The physics got harder to ignore. The measurement problem, the deep, central, embarrassing problem at the heart of quantum mechanics, turned out to be exactly the problem that Everett's interpretation solves. And as that realization spread, the many worlds interpretation went from curiosity to controversy to, for a growing number of physicists, the most likely description of how reality actually works. The most terrifying solution to the deepest puzzle in physics. And I call it terrifying not to be dramatic, but because when you actually follow the argument carefully, when you trace what it implies about the nature of reality, about personal identity, about what it means for something to happen, it is genuinely, viscerally, philosophically terrifying in a way that I think demands more than casual acknowledgement. So, let's go there carefully, from the beginning. Let me start with Schrödinger's cat, because it's the entry point, the thought experiment that makes the central puzzle of quantum mechanics impossible to ignore. Erwin Schrödinger proposed it in 1935, not because he thought it was a good description of reality, but as a reductio ad absurdum, as a demonstration that something must be wrong with the standard interpretation of quantum mechanics. Here's the setup. You have a cat in a sealed box. Inside the box, alongside the cat, is a radioactive atom, a Geiger counter, a vial of poison, and a mechanism connecting them. If the atom decays, a quantum mechanical event governed by probability, the Geiger counter detects it, triggers the mechanism, breaks the vial, and the cat dies. If the atom doesn't decay, the cat lives. Radioactive decay is a quantum mechanical process. In quantum mechanics, before measurement, a radioactive atom is not in a definite state of decayed or not decayed. It's in a superposition, a combination of both possibilities with specific probability amplitudes assigned to each. This is not a statement about our ignorance of the atom's actual state. It's a statement about the atom's actual state. The atom genuinely has no definite value for decayed or not decayed until a measurement is made. This is one of the most experimentally confirmed facts in all of physics. Now, the mechanism connects the quantum atom to the macroscopic cat. If the atom's decay triggers the mechanism, the cat dies. But before you open the box, before you make an observation, the atom is in superposition. And if the cat's fate is connected to the atom's state, and the atom is in superposition, then by the standard rules of quantum mechanics, the cat is also in superposition. Simultaneously, alive and dead. Both states with their associated probability amplitudes existing together in the quantum description of the system. You open the box, you find the cat either alive or dead, one definite outcome. The superposition has resolved into a single reality. Schrödinger's point was, this is absurd. Cats are not alive and dead simultaneously. Things have definite states. Quantum mechanics, applied to the cat, gives an absurd result. Therefore, something must be wrong with how we're applying quantum mechanics. He was right that something was wrong. What he didn't anticipate, what nobody anticipated in 1935, was just how wrong things would get when you really tried to fix it. To understand what's at stake, I need to explain the measurement problem precisely because it's often glossed over, described as a philosophical puzzle, a matter of interpretation, something physicists disagree about, but that doesn't affect predictions. All of that is misleading. The measurement problem is a genuine technical physical problem with the structure of quantum mechanics itself, here's the problem. Quantum mechanics has two modes of evolution. The first mode is the Schrödinger equation, the equation that governs how quantum states evolve in time. It's linear, deterministic, and continuous. If a system starts in a superposition, the Schrödinger equation evolves that superposition smoothly and deterministically. The superposition doesn't collapse. It just keeps evolving, spreading, entangling with its environment, becoming a more and more complex superposition of more and more things, but always a superposition, always both possibilities, evolving together. The second mode is wave function collapse, what happens during a measurement. When you measure a quantum system, the superposition apparently collapses to a single definite outcome. The cat is found alive, not in a superposition of alive and dead. The electron's position is measured to be here, not in a superposition of all positions. The indefiniteness resolves into definiteness. These two modes are inconsistent. The Schrödinger equation never produces collapse. A measurement is a physical interaction. It's atoms in the measuring device interacting with atoms in the system being measured. Physical interactions are described by the Schrödinger equation. So the Schrödinger equation should govern measurements, and the Schrödinger equation never gives collapse. The standard textbook treatment simply asserts that collapse happens during measurement without explaining how. It's a rule added to the theory by hand, without derivation, without mechanism. Copenhagen interpretation, the dominant interpretation taught in most physics courses, essentially says, apply the Schrödinger equation until you make a measurement, then apply the collapse rule, and don't ask what happens in between, or why the collapse happens, or what makes something a measurement, rather than an ordinary physical interaction. This is deeply unsatisfying. And for decades, most physicists accepted it not because it was satisfying, but because it worked. The predictions were right. The experiments confirmed the theory. Why worry about the mechanism? But there's a problem with not worrying. The measurement problem is not just a philosophical discomfort. It's a gap in the theory, a place where the theory doesn't tell you what happens. And gaps in theories lead to wrong predictions when you probe them carefully enough. Hugh Everett was 25 years old when he decided not to accept the measurement problem. Instead, he asked, what if the Schrödinger equation is always right? What if there's no collapse? What if we take the mathematics of quantum mechanics completely seriously and follow it wherever it leads? Here's what happens when you do that. Take the Schrödinger's cat experiment. Before you open the box, the atom is in superposition, decayed and not decayed, simultaneously. The cat is connected to the atom, so the cat enters a superposition alive and dead. The Schrödinger equation governs everything, including the cat. Now you open the box. You look. What happens? In the Copenhagen interpretation, collapse happens. The superposition resolves. You see a definite cat alive or dead. In Everett's interpretation, no collapse happens. The Schrödinger equation continues to govern everything, including you. When you look in the box, you become entangled with the cat. The superposition doesn't collapse, it expands. Now there's a superposition of two states, you seeing a live cat and you seeing a dead cat. Both states exist in the quantum description. Both are real. Both follow from the Schrödinger equation without any collapse, without any added rule. But in each of those states, there's a definite version of you having a definite experience. The version of you in the live cat branch sees a live cat. The version of you in the dead cat branch sees a dead cat. Each version is unaware of the other they've evolved, apart from the moment of branching, no longer able to interact. This is the many worlds interpretation. Not many worlds in the sense of different planets or different galaxies. Many branches of the quantum wave function, each one equally real, each one containing a different outcome of every quantum event. Every time a quantum superposition interacts with a larger system, every time something that could be called a measurement occurs, the wave function branches, all outcomes happen in separate non-communicating branches. There is no collapse. There is no randomness. There is just the Schrödinger equation relentlessly evolving the wave function of the universe into an ever more branching structure of realized possibilities. Let me try to make this more vivid with a thought experiment. Because I think the abstract description branches of the wave function can make it feel like a mathematical abstraction rather than a statement about reality. And the many worlds interpretation is, above all else, a statement about reality. Imagine the simplest possible quantum measurement. An electron can have spin up or spin down. You measure it. In quantum mechanics, before the measurement, the electron is in a superposition of spin up and spin down. In the Copenhagen picture, you measure the wave function collapses. You get spin up with 50% probability or spin down with 50% probability. The other outcome simply doesn't happen. The other branch simply doesn't exist. In the Everett picture, you measure. Your measuring device interacts with the electron. Your measuring device becomes entangled with the electron. Now, there's a superposition. Measuring device reading up, entangled with electron spin up, and measuring device reading down, entangled with electron spin down. You look at the measuring device, you become entangled with it. Now there's a superposition, you reading up and you reading down. Both branches exist, both are real. The U reading up has no access to the U reading down. They've separated. They're in different branches of the quantum state of the universe. And here's the thing. From the perspective of each branch from the inside, everything looks exactly as it would in the Copenhagen picture. The U in the up branch has a definite experience. You measured spin up. The measurement was definite. You got an outcome. There's no trace of the other branch in your experience, because decoherence, the process by which quantum superpositions lose their ability to interfere, has made the branches effectively independent. You're not aware of your other branch self. You never will be. But your other branch self exists right now, having the experience of measuring spin down, just as real as you, just as definite, just as unaware of you. Now I need to introduce decoherence, because it's the technical mechanism that makes the many worlds interpretation work as a physical theory rather than just a philosophical picture. And it's one of the most beautiful and important developments in the foundations of physics in the last 50 years. Decoherence is what happens when a quantum system interacts with a large complex environment. The environment, air molecules, photons, thermal fluctuations, interacts with the quantum system and becomes entangled with it. As the entanglement spreads through the environment, the different branches of the superposition become orthogonal, mathematically perpendicular in the Hilbert space that describes the quantum state. Once branches are orthogonal, they can no longer interfere with each other. They can no longer produce the interference patterns that are the hallmark of quantum superposition. From the perspective of any observer in one branch, the other branches effectively don't exist. Not because they've disappeared, they're still there in the wave function, but because they're orthogonal, no observation in one branch can detect any influence from the other branches. They're causally decoupled. Decoherence happens extraordinarily fast for macroscopic objects. The timescale for a dust grain to decohere, to lose its quantum character due to interactions with surrounding air molecules, is about 10⁻31 seconds. Incomprehensibly fast. For a cat or a human, the decoherence time is so short that it's physically meaningless to speak of macroscopic superpositions persisting. By the time any observation could be made, the branches have already completely separated. This explains why we never see Schrödinger's cat in a superposition of alive and dead. Not because the superposition doesn't exist, it does, in the quantum wave function. But because decoherence has separated the branches so completely that no observer in any branch can see the superposition, each observer sees a definite cat. Because each observer is already in a branch where the cat is definite. Decoherence is the mechanism that makes quantum mechanics look like classical physics at macroscopic scales. It's the bridge between the quantum world of superpositions and the classical world of definite outcomes. And it's fully derivable from the Schrödinger equation, no collapse required, no additional rules, just the same equation applied to larger and larger systems. Now I want to address the question that I suspect is forming in most minds at this point. The question that, when you really sit with it, is the most unsettling thing about the many worlds interpretation. If all outcomes happen, if there's a branch where you make every possible choice, where every possible event occurs, then what determines what you experience? If the U measuring spin up and the U measuring spin down both exist, both are real, both experience definite outcomes, then what made your particular experience happen? Why did you get spin up and not spin down? In the Copenhagen interpretation, this question has a specific answer: randomness. The collapse of the wave function is fundamentally random. Spin up happened with 50% probability, and it happened. Spin down didn't. The randomness is irreducible. It's built into the theory. It's not explainable by any deeper mechanism. It just happened. In the many worlds interpretation, the question is more subtle. Both outcomes happen. There is no randomness. The Schrödinger equation is completely deterministic, but there is branching. And the question of why you ended up in this branch rather than the other is a question about personal identity across branches, not a question about random events. And here's where the many worlds interpretation gets genuinely philosophically demanding. Before the measurement, there is one you. After the measurement, there are two yous, one in the spin-up branch, one in the spin-down branch. Both have continuity with the pre-measurement you. Both remember being the pre-measurement you. Both are legitimate continuers of the pre-measurement you. There is no fact of the matter about which one is really you, because both are equally real, both are equally continuous with the pre-measurement you. This is not just strange. It's a direct challenge to our ordinary concept of personal identity. We assume that personal identity is single, that there's a fact of the matter about which future person is you. The many worlds interpretation says, for quantum branching events, there is no such fact. Both branches are equally you until the branching, and after the branching, they're equally real continuers of. Let me tell you about why so many serious physicists have been drawn to Everett's interpretation, despite or because of its disturbing implications. Because the list of its defenders is not a list of fringe thinkers. It includes some of the most distinguished physicists alive. David Deutsch, the Oxford physicist who pioneered the theory of quantum computing, is perhaps the most eloquent defender of many worlds. Deutsch argues that quantum computers only make sense if the parallel branches are real, that quantum computation exploits the computational resources of the many worlds, using them to perform calculations in parallel across branches. If the branches didn't exist, quantum computation would be a miracle, an exponential speed-up with no mechanism to produce it. The branches are the mechanism. The many worlds are the computational resources that quantum computers exploit. Sean Carroll, theoretical physicist at Johns Hopkins and one of the most prominent science communicators in physics, has become an increasingly vocal defender of many worlds. Carroll argues that many worlds is the only interpretation that takes quantum mechanics seriously, that doesn't add extra rules, extra mechanisms, extra ontology to the theory. It's just quantum mechanics applied consistently all the way down. Max Tegmark, cosmologist at MIT, has taken the many worlds interpretation and extended it to what he calls the mathematical universe hypothesis, arguing that not just the branches of the quantum wave function, but all mathematically consistent structures are physically real. The multiverse of eternal inflation, the many worlds of quantum mechanics, and all possible mathematical structures, all equally real, all existing in a universe that is at its deepest level, pure mathematics. And Steven Weinberg, Nobel laureate, one of the architects of the Standard Model, wrote in his final book that he has reluctantly come to believe that many worlds is probably the right framework, despite finding it deeply unsatisfying. Weinberg's reluctant endorsement is significant precisely because of the reluctance if the man who helped build the Standard Model accepts many worlds despite finding it uncomfortable. That's evidence of how hard it is to avoid. Now I want to get to the deepest technical objection to many worlds, the one that even sympathetic physicists acknowledge is the hardest problem, the one that, if you're being completely honest, remains genuinely unsolved. It's the probability problem. And it cuts right to the heart of what the interpretation is claiming. In the Copenhagen interpretation, probabilities are fundamental. The Born rule, which says the probability of an outcome is proportional to the square of the amplitude of the corresponding wave function component, is simply stated as a fundamental rule of the theory. It's not derived from anything. It's just there as a postulate. In the many worlds interpretation, there's no randomness. Both outcomes happen. There are no probabilities in the fundamental evolution, just the deterministic Schrödinger equation. So where do the Born rule probabilities come from? Here's the problem in its sharpest form. Suppose you measure spin up or spin down with equal amplitudes, equal squared amplitudes. So equal Born rule probabilities. Both branches exist. In one branch, you got up. In the other, you got down. There are two versions of you. Why should the probability of finding yourself in the up branch be 50%? Naively, there are two branches, each with one version of you. So the probability of finding yourself in each is 50%, which happens to match the Born rule. But now, suppose the amplitudes are unequal. Suppose the amplitude for spin up is much larger than for spin down, so the Born rule probability of getting up is 90%. In many worlds, both branches still exist. There's still one version of you in the up branch and one in the down branch. Why should you be 90% likely to find yourself in the up branch? There are still just two branches, two versions of you, Naively, you should be equally likely to be in either branch. To recover the Born rule, many worlds needs to explain why branches with higher amplitude are more probable, even though both branches are equally real, equally existent. This is the probability problem, and it's genuinely hard. Several approaches have been proposed. David Deutsch and David Wallace have argued for a decision-theoretic derivation showing that a rational agent who believes many worlds is true must assign probabilities according to the Born rule, because any other assignment leads to irrational behavior. This argument is subtle and has been extensively debated. Some find it convincing, others find it circular. Another approach appeals to self-locating probability, the idea that even if all branches are real, you don't know which branch you're in, and the Born rule emerges from a specific way of reasoning about self-location under uncertainty. This approach connects to the philosophy of probability and has been developed by various theorists with mixed success. The honest answer is that the probability problem is not fully solved. There are promising approaches. There are serious arguments that the Born rule can be recovered from many worlds without being added as an extra postulate, but none of these arguments is universally accepted, and the debate continues. This is important to acknowledge. The many worlds interpretation is not a finished, closed theory. It's a framework with compelling advantages and remaining technical challenges. The probability problem is real, and anyone who tells you it's been definitively solved is overstating the case. But here's the flip side of that honesty. The competing interpretations have their own problems, and I think those problems are, in important ways, worse. The Copenhagen interpretation solves the measurement problem by not solving it. It asserts that collapse happens, but provides no mechanism, no dynamics, no physical description of when or how. It draws a line between quantum systems and classical observers, without explaining what that line is or where it lies. When pressed, Copenhagen advocates often say the interpretation is just a pragmatic tool, it gives correct predictions, and asking for more is a category error. This is an intellectually uncomfortable position for a theory that's supposed to describe what's actually happening. The pilot wave interpretation, developed by David Bohm in 1952, adds hidden variables to quantum mechanics. Particles have definite positions at all times, guided by a pilot wave that obeys a modified Schrödinger equation. The pilot wave interpretation solves the measurement problem and recovers Born rule probabilities. But it's explicitly non-local. The pilot wave for a particle depends instantaneously on the configuration of the entire universe. This non-locality is consistent with the observed violations of Bell inequalities, but it's deeply uncomfortable for anyone who believes in the spirit of special relativity. And it requires adding new variables, the particle positions that are in principle unobservable, which raises its own methodological questions. GRW theory, the Ghirardi-Rimini-Weber theory, modifies the Schrödinger equation by adding spontaneous collapse terms. Particles randomly collapse their wave functions with a specific rate and localization scale. This gives a definite mechanism for collapse, a genuine dynamical process, and makes macroscopic objects classical on the right time scale. But it modifies quantum mechanics, it adds new fundamental parameters, and predicts tiny deviations from standard quantum mechanical predictions that haven't been observed and are increasingly constrained by experiment. Every interpretation faces serious problems. The many worlds interpretation's problems are about probability and ontology, about what the branches are, how probabilities arise, and what it means for all branches to be equally real. The Copenhagen interpretation's problems are about mechanism and ontology, what collapse is, where it happens, what constitutes a measurement. The pilot wave's problems are about non-locality and the status of the hidden variables. GRW's problems are about the modification of quantum mechanics and the experimental constraints on that modification. There is no problem-free interpretation of quantum mechanics. The choice is not between a perfect theory and imperfect competitors. It's between different imperfect attempts to make sense of the most successful and most mysterious theory in physics. Now, I want to do something that I don't think gets done enough in discussions of many worlds. I want to talk about what it actually feels like to take it seriously, not as an intellectual exercise, but as a lived reality. If many worlds is right, then every decision you've ever made has branched the wave function. Every time you deliberated, considered alternatives, and chose, the other alternatives happened. In other branches, equally real, you made different choices. The you who chose to read this chose not to in another branch. The you who is in a relationship is not in another branch. The you who is alive there may be branches where you are not. This is not comfortable. Most people's first reaction is some version of, this can't be right, because it makes choices meaningless. If I choose X, then another me chooses Y, so what difference does it make? Why deliberate at all? But this reaction is based on a confusion. The fact that another branch exists in which you make a different choice doesn't make your choice meaningless in your branch. You still make a real choice in your branch. The consequences in your branch are real. Your experience in your branch is real. The other branches are real, but they're not your branches. They're inhabited by other versions of you who are making their own choices and experiencing their own consequences. David Deutsch addresses this beautifully. He argues that the many worlds interpretation doesn't undermine the significance of choices, it multiplies it. Your choices don't just affect one future, they affect which branches you and your descendants inhabit. The stakes are, in a sense, infinitely higher. This is a strange comfort, but it's one way of living with the many worlds picture without collapsing into nihilism. There's one more thing I want to introduce in this first part, because it connects the many worlds interpretation to everything we've been discussing in recent conversations: the nature of reality, the relationship between physics and experience, the question of what the universe actually is. The many worlds interpretation is, at bottom, a claim about the ontology of the wave function. It says the wave function is real. It's not a mathematical tool for calculating probabilities. It's a description of what actually exists, a vast high-dimensional object that evolves deterministically and contains all branches simultaneously. The wave function of the universe is a vector in an abstract space of unimaginably high dimensionality, Hilbert space. It's not in three-dimensional space. It's in a space with as many dimensions as there are possible quantum states of the universe, a number so large it defies description. And here's what's genuinely startling. If the wave function is real, then the three-dimensional space we experience is not fundamental. Our three-dimensional world, the world of rocks and trees and people and planets, is not the basic arena of reality. The basic arena of reality is Hilbert space. The three-dimensional world we experience is a structure that emerges from the wave function in a specific branch due to decoherence and the specific form of the laws of physics. Space itself is emergent, not fundamental, not the container in which physics happens, but a derived structure arising from the quantum state of the universe. We've encountered this theme before in our conversation about black holes and holography, where we found that space might emerge from quantum entanglement. The many worlds interpretation points in the same direction from a completely different angle. Space is not fundamental, the wave function is. And what we call the physical world, the world of definite objects in three-dimensional space, is what the wave function looks like from inside one of its branches. This is the picture that Everett's interpretation leads to when you follow it all the way. Not just many worlds, but a universe whose fundamental description is a quantum state in an abstract mathematical space from which space, time, and the appearance of a single definite reality all emerge. Terrifying in the most precise sense. Not because it's dangerous, because it's disorienting in the deepest possible way. It tells us that the world we thought we were in is not the world that actually is. The world that actually is vastly larger, vastly stranger, and contains vastly more than the one history we experience. All timelines are happening now, all of them, in the branches of the universal wave function, equally real, equally physical, equally you. In part 2, I want to go deeper into what this means for the structure of reality, for the relationship between quantum mechanics and cosmology, for the question of consciousness in a many worlds universe. And I want to tell you about the connection between many worlds and the multiverse of eternal inflation and what happens when you put them together. Because the result, quantum mechanics plus eternal inflation, gives a picture of reality so vast, so strange, so extraordinary that I genuinely don't know of any adequate human framework for comprehending it. But we're going to try. So we'd arrived at this place where the many worlds interpretation taken seriously, followed to its logical conclusions, tells us that the wave function of the universe is the fundamental reality, that three-dimensional space and the appearance of definite outcomes are emergent features of specific branches, and that every quantum measurement branches the universe into multiple equally real versions of what happens next. Now I want to push further into what the many worlds interpretation implies when you combine it with everything else we know, with cosmology, with the nature of consciousness, with the question of what it means for something to be real. And I want to get into the deepest technical challenge that the interpretation faces the preferred basis problem, because understanding it reveals something important about what the interpretation is actually claiming. But first, I want to address something that I think needs to be said clearly and honestly. Because the many worlds interpretation is sometimes presented as if it's obviously correct, as if the only reason anyone resists it is intellectual timidity or failure to follow the logic. That's not fair. The many worlds interpretation is genuinely controversial among the physicists who think most carefully about the foundations of quantum mechanics, not because they haven't understood it, because they've understood it and found problems that aren't easily dismissed. Let me engage with those problems seriously before I tell you why many physicists still think many worlds is the best available option. The preferred basis problem is perhaps the deepest technical challenge facing the many worlds interpretation, and it's the one that most clearly reveals what the interpretation is and isn't claiming. Here's the problem. The wave function of the universe exists in Hilbert space, an abstract high-dimensional space. In Hilbert space, there are infinitely many ways to decompose the wave function into branches. Not all of these decompositions correspond to anything we'd recognize as worlds. Some decompositions give you branches containing definite macroscopic classical-looking outcomes. Others give you completely different branches, branches that don't correspond to anything physical that we'd recognize. The question is, which decomposition is the right one? Which basis, which way of slicing the Hilbert space into branches corresponds to the actual branches of the many worlds? Why do we branch in terms of live cat and dead cat rather than in terms of some bizarre quantum superposition that has no classical analog? The answer that many worlds proponents give is decoherence. The interaction between quantum systems and their environments picks out a specific basis, the pointer basis, as the preferred one. The environment doesn't interact with all possible quantum states equally. It preferentially decoheres certain states, the ones that correspond to definite localized positions and energies, while leaving quantum superpositions of others intact. The branching we observe into classical-looking macroscopic outcomes is the branching that decoherence produces. This is a good answer. It's physically motivated, it's mathematically precise, and it explains why the branches look the way they do. But critics argue it's not complete. Decoherence selects an approximately preferred basis. It picks out a preferred direction in Hilbert space that corresponds roughly to classical outcomes, but it does so only approximately. The basis is never perfectly sharp. There's always residual ambiguity in exactly how to define the branches. For practical purposes, this ambiguity doesn't matter. The classical-looking branches are definite enough for any prediction we'd want to make. But for the foundational question of whether many worlds provides a clean, unambiguous picture of reality, the approximate nature of the preferred basis is a genuine concern. The branches are real, but their boundaries are fuzzy. And if the branches are fuzzy, it's not entirely clear how many of them there are, what their probabilities are, or exactly what all timelines are happening now means in precise mathematical terms. The philosopher of physics, David Wallace, who has written the most technically detailed defense of many worlds, acknowledges this. He argues that the fuzziness of the branches is not a bug, but a feature, that the classical world is inherently fuzzy at the quantum level, and that requiring sharp branch boundaries is demanding too much precision from an approximate description. The branches are real enough to make sense of the physics. They don't need to be exactly defined to play the role the theory assigns them. I find this response partially satisfying, but I want to be honest. The preferred basis problem is not fully resolved. The many worlds interpretation's account of why we have the branches we have and not some other set of branches relies on decoherence, and decoherence gives an approximate rather than exact answer. This is something to sit with rather than dismiss. Now let me tell you about something that connects the many worlds interpretation to the multiverse of eternal inflation that we discussed in our last conversation. Because when you put quantum mechanics and cosmology together, when you apply the many worlds interpretation to the wave function of the entire universe, including its inflationary history, you get something so extraordinary that it demands its own careful treatment. In our conversation about eternal inflation, we established that the universe is almost certainly vastly larger than what we can observe, an eternally inflating sea of space-time in which our observable universe is one bubble among infinitely many. Different bubbles have different physical constants, different effective laws of physics, different histories. Now apply the many worlds interpretation to this eternal inflation. In many worlds, every quantum event branches the wave function. Eternal inflation is driven by quantum events, specifically the quantum fluctuations of the inflaton field that determine when and where inflation ends, when and where bubbles form. In many worlds, every quantum fluctuation that could have gone differently generates a branch. Every bubble that forms in a branch. Every bubble that doesn't form in some branch forms in another. The result is a wave function of the universe that branches not just at the level of individual measurements in laboratories, not just at the level of Schrödinger's cat, but at the level of entire universes. Each branch of the cosmic wave function contains a different history of eternal inflation, a different pattern of bubbles, a different collection of pocket universes. The combination of many worlds and eternal inflation gives you what Max Tegmark calls the level 3 multiverse, the quantum mechanical multiverse embedded within the level 2 multiverse, the inflationary multiverse. The level 2 multiverse says there are many bubbles with different physical constants. Many worlds says that in each of those bubbles, every quantum event branches the wave function, creating further multiplicity within each bubble. The total structure is not just many universes. It's an unimaginably vast hierarchy of branching histories, each branch containing different physical laws, different histories, different collections of intelligent beings, all of them equally real, all of them instantiated in the branches of the universal wave function. This is where the picture becomes genuinely dizzying, and I think it's important to sit with the vertigo rather than resolve it too quickly with reassuring words, because the vertigo is appropriate. The picture is that vast, that strange, that different from anything our intuitions were built to handle. Now let me address consciousness. Because the many worlds interpretation has a very specific relationship with the nature of mind that I think is important to understand. In the Copenhagen interpretation, measurement plays a special role. Collapse happens when a measurement is made. And measurement sometimes gets glossed as observation by a conscious observer. The idea that consciousness is somehow required to collapse the wave function to bring definite reality into existence. This is the most controversial version of Copenhagen, sometimes called the consciousness causes collapse interpretation, and most physicists reject it precisely because it makes consciousness fundamental to physics in a way that's deeply problematic. The many worlds interpretation sidesteps this entirely. There's no collapse, there's no measurement problem, there's no special role for consciousness. The Schrödinger equation evolves the wave function, and everything, including conscious observers, is part of that wave function. Consciousness is not required for branching. Branching happens whenever any quantum system with sufficient complexity interacts with any other. A rock, a photon detector, a thermostat, all of these decohere the wave function and create branches with no consciousness required. Consciousness in many worlds is just a physical process, a complex information processing system embedded in the wave function, evolving according to the Schrödinger equation like everything else. It has no special ontological status. It doesn't collapse anything. It just happens in every branch where the physical conditions for it are met. But here's where something interesting appears. In the many worlds picture, consciousness is a pattern, a specific kind of information processing structure that can be realized in many different branches. The U in the spin-up branch and the U in the spin-down branch are both realizations of the same pattern in different branches. They're different instantiations of the same cognitive structure, diverged from a common ancestor at the moment of branching. This connects to our conversation about consciousness and personal identity. We established that the question, "Where is your mind?" might not have a simple answer, that consciousness might be substrate independent, a feature of certain information processing patterns rather than of specific physical substrates. In the many worlds picture, consciousness is pattern instantiated. It's what certain branches of the wave function look like when they contain the right kind of complexity. And here's a thought that I find genuinely extraordinary. In the many worlds interpretation, consciousness is not rare in the universe. It's multiply instantiated in every branch where the conditions for it are met, consciousness arises. The total amount of consciousness in the universe, the total number of branches containing observers, is vastly larger than any single branch estimate would suggest. Every branching event that produces a conscious observer produces all the possible observers in all the possible branches. The universe, in the many worlds picture, is saturated with consciousness, not in any mystical sense, but in the specific physical sense that the wave function contains infinitely many branches, in many of which the conditions for conscious information processing are met, Let me now tell you about something that I think is the most practically significant consequence of many worlds. Something that connects the interpretation to technology that exists right now, that you might have heard about, that is already being built, quantum computing. A quantum computer exploits the superposition and entanglement properties of quantum mechanics to perform certain computations exponentially faster than any classical computer. The most dramatic example is Shor's algorithm, a quantum algorithm that can factor large numbers exponentially faster than any known classical algorithm, with implications for encryption and cryptography. Why is a quantum computer so much faster? The naive answer, that it tries all possibilities simultaneously, is both approximately right and potentially misleading. But let me give you the many worlds version, which I think is the most illuminating in a quantum computer. The qubits, the quantum bits, are prepared in superpositions and entangled with each other. The computation is a quantum circuit, a sequence of quantum gates that transforms the initial state. The output is measured, giving a definite answer. From the Copenhagen perspective, the speed-up seems almost magical. The quantum computer somehow explores exponentially many computational paths corresponding to the exponentially many states in the superposition and finds the answer, but the collapse picture provides no mechanism. The computation happened in superposition and then collapsed to an answer. How? From the many worlds perspective, the mechanism is clear. The quantum computation proceeds in all branches simultaneously. In each branch, the computation follows a specific path through the state space. The branches interfere constructively in the right answer, destructively in the wrong answers, and the final measurement picks up the answer that interference has amplified. The exponential speedup comes from exploiting the computational resources of the many branches from doing exponentially many computations in parallel across branches. David Deutsch makes this argument forcefully. If you don't believe in the many branches, you have no explanation for where the quantum speedup comes from. You've measured an exponential speedup in computation that, according to Copenhagen, happened in a superposition, which is just a way of saying it happened without explaining how. Many worlds provides the mechanism. The computation happened in all branches, and we harvested the result. This is not just a philosophical argument. Quantum computers exist. They're being built right now by Google, IBM, Microsoft, Amazon, and dozens of other companies and research institutions. The quantum advantage, the exponential speedup, is not theoretical. It's been demonstrated in specific, narrow computational tasks, and the effort to extend it to practical problems is one of the major technological races of our era. And if many worlds is right about quantum computation, if the many branches are what provides the computational resource, then quantum computing is not just a technology. It's direct experimental evidence for the reality of the many branches. Every time a quantum computer exploits its exponential speedup, it's exploiting the many worlds. Now I want to take you somewhere that most discussions of many worlds don't go into what the interpretation implies about the arrow of time. We've established in various conversations that the second law of thermodynamics tells us entropy increases over time, that physical systems evolve from lower entropy to higher entropy states. This gives us the arrow of time, the direction in which time flows, the reason we remember the past and not the future. But the fundamental equations of physics, including the Schrödinger equation, are time symmetric. They look the same whether you run them forward or backward. The arrow of time is not built into the fundamental dynamics. It's an emergent property. It arises from the specific initial conditions of the universe, which had extraordinarily low entropy at the Big Bang. In the many worlds picture, this gets an interesting twist. The Schrödinger equation is perfectly time symmetric. It runs equally well in both directions. But the branching process, the decoherence that separates branches, is effectively irreversible. Once branches have separated, they don't remerge. The information about which branch you're in spreads into the environment through decoherence, and recovering that information would require reversing all the interactions between the system and its environment, a practical impossibility. This effective irreversibility of branching is connected to, but not identical with, the second law. In the many worlds picture, the arrow of time has two components: the thermodynamic arrow, the increase of entropy, and the branching arrow, the growth of the number of branches over time. Both arrows point in the same direction toward the future, and both are consequences of the same initial conditions, the low entropy, low branching state of the universe at the Big Bang. An interesting consequence: in the very far future, As the universe approaches heat death, maximum entropy, minimum free energy, the branching rate doesn't stop. Quantum fluctuations continue. The wave function continues to branch, but the branches become less and less distinguishable. They all look like the same featureless high entropy state. The branching continues, but its products are increasingly indistinguishable. This gives a very specific picture of the far future of the universe in many worlds. Not just a single heat death state, but an enormous, constantly branching wave function, all of whose branches look like the same featureless equilibrium. An infinite proliferation of branches, all identical. There's something both profound and melancholy about this picture. The universe's future is not a single cold void, it's an infinite multiplication of identical cold voids. I want to address something that I think is genuinely important and that defenders of many worlds sometimes understate: the ontological cost of the interpretation. When Occam's razor is applied to physical theories, when we try to choose the simplest explanation, the usual metric is simplicity of laws. Many worlds has extraordinarily simple laws, just the Schrödinger equation applied universally without additions. By this metric, many worlds is the simplest possible interpretation. It adds nothing to the mathematics. But Occam's razor also applies to ontology, to the entities posited to exist. And by this metric, many worlds is not simple. It posits an unimaginably vast number of entities, all the branches of the universal wave function, all the versions of you and me and every other observer, all the parallel histories. This is a genuine cost. The interpretation is parsimonious in its laws, but extraordinarily extravagant in its ontology. Whether this is acceptable depends on what you think Occam's razor is really saying, whether simplicity of laws or simplicity of ontology should take priority. Many worlds advocates typically argue that the entities, the branches, are not separately postulated. They follow from the mathematics. You don't add the branches by hand. The branches emerge from the Schrödinger equation applied to the initial state. So, in a sense, the ontological extravagance is not a cost of the interpretation, but a consequence of the mathematics. If you believe the mathematics describes something real, the branches come for free. But this argument has a response. The claim that the branches are real, that they represent genuinely existing physical worlds, is itself a philosophical commitment. The mathematics of quantum mechanics doesn't, by itself, tell you what's real. It tells you what the mathematical structure is. The interpretation, the claim that all branches are equally real physical worlds, is an added assumption, and that assumption brings the ontological cost. This is not a decisive objection. Every interpretation of quantum mechanics adds something to the bare mathematics. Copenhagen adds the collapse rule and the mind-world boundary. Pilot wave adds hidden variables. GRW modifies the dynamics. Many worlds adds the ontological commitment to the reality of all branches. The question is which additional commitments are most justified, most coherent, most empirically adequate. My honest assessment is that many worlds adds the smallest amount to the mathematics, just the claim that the mathematics is complete, that it describes everything there is. But that smallest addition has the largest ontological consequences. It turns one world into infinitely many. Let me now connect many worlds to something that I think is philosophically underexplored: the relationship between the interpretation and what we mean by explanation in physics. We often say that science explains phenomena by showing that they follow from deeper principles, by deriving them from more fundamental laws. The expansion of the universe follows from general relativity. The periodic table follows from quantum mechanics. The second law follows from statistical mechanics and initial conditions. In this framework, explanation is about derivation. You explain something by showing it's a consequence of something more fundamental. Many worlds offers a specific kind of explanation for why we observe definite outcomes in quantum measurements. We observe definite outcomes. We see a cat that's definitely alive or definitely dead because we're in a branch where the decoherence has selected a definite outcome. The definiteness is a consequence of our being in a particular branch, not a fundamental feature of reality. But here's the interesting twist. The explanation for why we're in this branch, why we're seeing this particular outcome rather than another, is not a causal explanation. There's no physical process that selected this branch. All branches exist. We're in this one simply because this is the branch in which we find ourselves. The explanation is not causal but locational. We're here because this is where we are. This is a genuinely different kind of explanation from what physics usually offers. It's more like the anthropic explanation we discussed in our conversation about eternal inflation. We observe what we observe because we're the observers who are here in this branch observing this. Both eternal inflation and many worlds ultimately converge on this type of explanation for certain facts about our experience, not causal derivation from deeper principles, but selection from a vast space of possibilities. The facts we observe are not the only facts that exist. They're the facts in our corner of the multiverse, in our branch of the wave function. This convergence between the two most radical ideas in modern theoretical physics, eternal inflation and many worlds on the same type of explanation, is striking. It suggests that this type of explanation selection from possibility may be more fundamental than traditional causal explanation at the deepest levels of physical theory. I want to close this second part with something that brings the whole discussion back to the specific question we started with: the cat, the box, the measurement. Schrödinger designed his thought experiment to show the absurdity of quantum mechanics applied to macroscopic objects. He expected that the absurdity would motivate physicists to fix quantum mechanics to find a theory that didn't produce superpositions of live and dead cats. What happened instead is remarkable. Physicists tried many different fixes: Copenhagen, pilot wave, GRW, and others. And one of them, Everett, decided not to fix quantum mechanics, but to take it seriously. To say the cat is in a superposition. Both states are real. The superposition doesn't collapse. What happens when you open the box is that you become entangled with a cat, and there's a branch in which you see a live cat and a branch in which you see a dead cat, and both are equally real. Schrödinger's reductio ad absurdum became, in Everett's hands, a direct description of reality. And here's what I find genuinely extraordinary about this. The thing that seemed most absurd macroscopic superpositions, cats that are alive and dead simultaneously, turns out to be exactly what quantum mechanics predicts when you take it seriously. The absurdity doesn't disappear. We just learn to locate it correctly. The absurdity is not in the theory. The absurdity is in our intuitions built by evolution for a classical world equipped to handle definite outcomes in single histories wholly inadequate for the quantum reality that underlies them. Taking quantum mechanics seriously required giving up something we value deeply: the uniqueness of experience. The sense that there is one world, this world, and that what happens happens and what doesn't happen doesn't. Everett's answer is: what happens is everything. All of it, in all branches simultaneously. And what you experience is your local slice of the wave function, your branch, which looks definite because you're entangled with your environment in a definite looking way. All timelines are happening now. Not because of some mystical principle, not because of any exotic physics, because the Schrödinger equation is linear and the universe is quantum mechanical and there's no collapse. In part 3, I want to bring this all the way home to the question of what many worlds means for you specifically, personally, for how you should think about your choices, your identity, your mortality. And I want to explore something that I've been building toward throughout this conversation: the question of what the many worlds interpretation implies about the nature of reality itself at the deepest level. Whether the wave function is fundamental, or whether the wave function is itself an approximation to something even more fundamental that we haven't yet found. Because many worlds, for all its radicalism, might not be the final word. It might be the second to last layer correct as far as it goes, but pointing at something deeper. So we'd arrived at this place where the many worlds interpretation is not just a philosophical curiosity, it's a serious, mathematically grounded attempt to take quantum mechanics completely seriously, with consequences so radical that they challenge every intuition we have about the nature of reality, personal identity, and the meaning of choice. Now I want to bring it home to what this means for you, for the specific, embodied, experiencing person reading these words right now, because I think the philosophical implications of many worlds, when followed carefully, without flinching, are more personally confronting than any other idea in modern physics. More confronting than the Big Bang, more confronting than black holes, more confronting even than the multiverse of eternal inflation, because those ideas are about things that are far away, long ago, cosmically distant from daily life. Many worlds is about this, about now, about every decision you make and every quantum event that's happening in your body at this moment. Let me start with the most personal version of the question. What happens to you, to your specific continuous sense of being you in the many worlds picture? Right now, in your body, quantum events are occurring constantly. Ions crossing cell membranes through quantum tunneling, photons being absorbed by retinal molecules in your eyes through quantum processes. enzyme catalysis involving quantum tunneling of protons and electrons, neural processes that, while largely classical, are built from quantum mechanical components. Every one of these quantum events in the many worlds picture has multiple possible outcomes. Every one of those outcomes is realized in some branch. This means you are branching constantly, not occasionally, not once per major life decision, but continuously at a rate determined by the quantum mechanical processes in your body and environment. The number of branches containing distinct versions of you is not 2 or 10 or 1,000,000. It's unimaginably large. The branching is happening faster than any process in your experience can track. And each of those branches contains a version of you with a continuous memory, a version of you who has a completely consistent, seamless narrative of being the same person who woke up this morning, who has been following this video, who has been thinking these thoughts. Each version is as genuinely continuous with the pre-branching you as every other. Each has an equal claim to being you. Now here's where the personal confrontation really begins. In some branches, not all, because the probability amplitudes must be right, and the Born rule must be derivable in some branches, you are not alive, not because of any exotic quantum event, simply because the quantum mechanical processes governing your biology took a different path. A cell division that happened one way in your branch happened another way in another branch, leading to a mutation, leading eventually through a long chain of causation to a different health outcome. In the many worlds picture, the branches where you die at some point in the near future are real branches. They exist. Versions of you inhabit them up to the moment of death, experiencing a completely seamless, continuous, subjective narrative that leads to that ending. And versions of you inhabit branches where you live far longer, where the quantum events break differently in your favor, where the biological machinery that might have produced disease instead remains healthy. All of these branches exist. All of them are happening now. The physicist Hugh Everett himself, the man who invented the many worlds interpretation, thought about this question, and his response, which some people find consoling and others find horrifying, was this. Everett believed in what's sometimes called quantum immortality. The argument goes like this. In the many worlds picture, there is always some branch in which you survive any given event. Even events with overwhelmingly high probability of death have some branches where you survive because the quantum mechanical processes governing the event have non-zero amplitude for survival outcomes. The set of branches where you die is real, but so is the set of branches where you don't. From a third-person perspective from outside, looking at all branches, you die in most of them. But from a first-person perspective, from inside the sequence of experiences, you always find yourself in a branch where you're still alive. Because dead versions of you have no experiences. The only branches you can be experiencing from the inside are the ones where you're still alive. This is the quantum immortality argument. And it's genuinely unsettling, not because it's comforting, but because it's the opposite of comforting when you really follow it. Because surviving in some branch does not mean surviving well. The branches where you survive an otherwise lethal event may be branches where the survival came at enormous cost, severe injury, profound loss, extreme circumstances. The set of surviving branches is not a set of good branches. It's simply a set of branches where you're still alive. And as you continue to survive, as the branching continues, the branches where you're alive but flourishing become a smaller and smaller fraction of all surviving branches. Everett himself seemed to have internalized this in a strange way. He was known for reckless behavior, heavy drinking, smoking, lack of concern for his health. Whether or not this was connected to his quantum immortality beliefs is impossible to know, but he died at 51 of a heart attack. In many branches, he died later. In many branches, earlier. In the branches we're in, the ones where his ideas survived and were eventually recognized, he died at 51. I don't want to dwell on quantum immortality as a practical belief system. I think it would be deeply irresponsible to take it as a guide to action, to treat it as license for reckless behavior on the grounds that some branch of you will survive. The branches where you survive stupid risks are not branches you'd want to inhabit. And the you in those branches can't communicate with the you in the branches where recklessness led to death. But I think the quantum immortality argument is worth understanding precisely because it illustrates how deeply many worlds challenges our ordinary concepts of personal identity, survival, and what it means for something to matter. Let me now turn to something more philosophically productive, the question of what choices mean in the many worlds picture and whether they mean more or less than in a single world picture. I raised this briefly in part 1, and I want to address it more carefully here. Because the intuition that choices don't matter in many worlds because all outcomes happen anyway is both understandable and, I think, fundamentally confused. Here's why it's confused. The claim that all outcomes happen doesn't imply that outcomes don't matter. It implies that all outcomes are real. But the realness of all outcomes doesn't diminish the realness of any particular outcome, including the outcome in your branch. Consider an analogy. In the eternally inflating multiverse, there are infinitely many universes where every possible physical event occurs. In some of those universes, every atom is arranged in exactly the configuration that corresponds to you reading these words. In others, every atom is arranged differently. Does the existence of all these other universes make your experience less real? Does it make this moment less significant? No. The significance of this moment is a feature of this moment, of this branch, this configuration, this experience. The existence of other branches doesn't dilute its significance. It just expands the total scope of what exists. The same applies to choices. When you deliberate, when you weigh options, consider consequences, and make a decision, you are determining which branch you inhabit. You don't determine whether the other branches exist. They do, regardless of what you decide, but you do determine what happens in your branch. And your branch is the one you experience. Your branch is where your life happens. Your branch is where your relationships exist, where your achievements matter, where your suffering is real. David Deutsch makes this point with particular force. He argues that many worlds doesn't undermine the significance of choices, it reveals their true scope. In a single world picture, a choice determines one outcome among alternatives that never happen. In many worlds, a choice determines which branch you inhabit among alternatives that all happen. The stakes are, in a sense, infinite. Your choices affect not just your outcome, but the outcome in every branch that follows from your present branch. The choices ripple forward through the branching structure of the wave function. This is a genuinely different way of thinking about moral responsibility. Your choices don't cause some outcomes and prevent others. All outcomes happen somewhere, but your choices determine your trajectory through the branching structure. They determine what kind of agent you are, what branch you inhabit, what version of events your experience constitutes. Now, let me address something that I think is the deepest philosophical challenge that many worlds faces, deeper than the probability problem, deeper than the preferred basis problem. It's the question of why we should care. If all branches are equally real, if the version of me that makes a terrible choice is just as real as the version that makes a good one, then what grounds ethical obligations? What grounds the claim that I should try to be good, to help others, to make wise choices? If there's a me in every branch and all those me's are equally real, and there's no fact of the matter about which me is really me, then why does it matter what this me does? This is the challenge that many critics of many worlds see as decisive. The interpretation seems to dissolve the basis for caring about outcomes, for taking responsibility, for moral effort. But I think this challenge, while real, is answerable. And the answer reveals something important about the relationship between physics and ethics. Ethics is not grounded in physics. Ethics is grounded in values, in what matters to conscious beings who have experiences, who can flourish or suffer, who have relationships and projects and goals. The physical structure of reality, whether it's one world or many, doesn't determine what matters. It determines what exists. In many worlds, what exists includes all branches. But what matters is still what matters to the beings in each branch. The version of me in this branch can suffer. The people I care about in this branch can suffer. The projects I value in this branch can fail or succeed. These things matter to me in this branch regardless of what's happening in other branches. The existence of other branches doesn't make my branch's suffering less real or less worth preventing. This is the key move. Moral concern is first person and present. It's about what matters from the inside of a particular stream of experience. Many worlds tells us that there are infinitely many such streams. But it doesn't tell us that any one of them matters less because others exist. Each stream is the whole of experience from its own perspective. The many worlds interpretation is therefore not a threat to ethics. It's compatible with robust moral concern with the conviction that what happens in this branch to these people in this moment matters. The universe's branching structure is simply the backdrop against which our ethical lives unfold. It doesn't dissolve our responsibilities, it contextualizes them. Let me now tell you something about the future of the many worlds interpretation, about where the research is going, about what would convince more physicists, and about whether the interpretation can ever be definitively confirmed. The honest answer to can many worlds be confirmed is not directly. We cannot observe other branches. We cannot detect the splitting of the wave function as it happens. We cannot communicate with other branch versions of ourselves. The branches are, by construction, causally decoupled once decoherence has occurred. But there are indirect approaches that could provide evidence, not definitive proof, but increasing confidence. The most promising involves quantum computing. As quantum computers become more powerful, as they demonstrate quantum advantage in more complex and practically significant tasks, the many worlds account of where the speed-up comes from becomes more compelling. If you're a Copenhagen advocate who claims no branching is happening, you have an increasingly difficult time explaining how the quantum computer achieved its exponential speed-up. The many worlds account, the computation happened in parallel across branches, becomes more natural as the quantum advantage becomes more dramatic. A second approach involves testing the linearity of quantum mechanics. The Schrödinger equation is linear, superpositions are maintained and evolve smoothly. Any deviation from linearity would be evidence against many worlds, evidence that the Schrödinger equation breaks down, that some modification of quantum mechanics is needed, that perhaps GRW-type spontaneous collapse is occurring. Experiments have been pushing the boundaries of quantum superposition to larger and larger scales, maintaining coherence in molecules, in superconducting systems, in mechanical oscillators. So far, linearity holds. Every experiment confirms that quantum mechanics, and therefore the branching structure applies to larger and larger systems. A third approach involves the cosmological implications of many worlds. Combined with eternal inflation, many worlds makes specific statistical predictions about what observers should expect to see about the distribution of physical constants, about the prevalence of certain types of cosmological structures, about what a typical observer's experience should look like. These predictions are difficult to test, partly because of the measure problem, but they're not entirely empty. Future cosmological observations might constrain the combined multiverse picture in ways that favor or disfavor many worlds. Now let me tell you about something that I've been saving for the end, because it's the most radical possibility of all, and it requires everything we've built up to appreciate it fully. Many worlds takes quantum mechanics seriously by saying the wave function is real and the Schrödinger equation always applies. But this raises a question that many worlds itself doesn't answer. What is the wave function fundamentally? The wave function is a mathematical object, a vector in Hilbert space. It assigns complex numbers and amplitudes to every possible configuration of the universe. It's an extraordinarily abstract thing. When we say the wave function is real, we're saying this abstract mathematical object corresponds to something in physical reality. But what? The wave function doesn't live in three-dimensional space. It lives in a configuration space with as many dimensions as there are degrees of freedom in the universe, an astronomical number of dimensions. The three-dimensional space we experience is not where the wave function lives. It's a structure that emerges from the wave function in specific branches. David Wallace and Tim Maudlin have had a fascinating debate about exactly this. Maudlin argues that many worlds has not fully solved the ontology problem. It hasn't told us what the wave function is, what it's made of, what it means for an abstract mathematical object to be real. Wallace argues that the wave function's reality is demonstrated by its causal role. It's real because it does things, because the structures in Hilbert space correspond to physical structures in the world we observe. But here's what I find most interesting. The wave function in Hilbert space, the quantum states, the amplitudes, all of this is mathematical structure. Max Tegmark has argued in his mathematical universe hypothesis that mathematical structure just is physical reality, that the universe is, at its most fundamental level, a mathematical object, and everything that exists is a mathematical structure. In this view, the wave function is real because it's mathematical, and mathematical structures are real. This is the most radical version of the many worlds picture, the version where physics and mathematics become the same thing, where the distinction between the map and the territory dissolves, where what exists and what is mathematically consistent are identical. I'm not certain Tegmark is right, but I think this direction toward understanding physical reality as fundamentally informational or mathematical is where the deepest implications of many worlds are pointing. The same direction we arrived at from holography and black hole physics, from ADAS, CFT, and emergent spacetime. Different paths, same destination. Reality, at its most fundamental level, might be mathematical structure. And the many worlds are all the branches of that structure, all simultaneously, equally, irreducibly real. Let me come back now to Schrödinger's cat, to where we started. Schrödinger put the cat in the box to demonstrate an absurdity. A cat cannot be simultaneously alive and dead. Quantum mechanics applied to macroscopic objects gives an absurd result. The absurdity must reveal a flaw in the theory. Everett's response, 70 years later, was to accept the absurdity. The cat is simultaneously alive and dead in the sense that both branches of the wave function are real. There is a branch containing a live cat and a branch containing a dead cat. When you open the box, you become part of the entanglement. You branch along with the cat. You in one branch see a live cat. You in another branch see a dead cat. Both experiences are real. Neither is privileged. What Schrödinger saw as a reductio ad absurdum, Everett saw as a description. The quantum world is genuinely stranger than classical intuition allows. The task of physics is not to make quantum mechanics comfortable, to sand off its strange edges until it fits our classical intuitions. The task is to understand what quantum mechanics is actually saying, follow it wherever it leads, and update our intuitions accordingly. This is, I think, the deepest lesson of many worlds. Not the specific claim that all timelines are happening, though that might be true, but the methodological commitment: take the mathematics seriously. Follow the equations. Let reality be what the physics says it is, not what your intuitions say it should be. This is hard. It goes against everything our brains evolved to do. Our brains evolved to track one timeline, the timeline we're in, to remember the past and anticipate the future. To experience a single, continuous stream of consciousness in a single, definite world, the apparatus for experiencing multiple simultaneous realities simply doesn't exist in our cognitive toolkit. But the universe doesn't care about our cognitive toolkit. The universe is what it is. And what it appears to be, if the Schrödinger equation is always right, if there's no collapse, if the mathematics describes something real, is a vast, branching, continuously multiplying structure of realized possibilities, all happening simultaneously, all equally real, all inhabited by versions of every conscious being who has ever existed. All timelines are happening now. I said that at the beginning, and I want to say it again at the end, not as a slogan, but as the conclusion of a careful argument. The Schrödinger equation is linear. It has never been observed to fail. Every attempt to find a deviation, every experiment designed to catch the wave function behaving non-linearly, to observe the collapse, to see the quantum world fail to be quantum at large scales, has failed to find one. The quantum world is quantum, all the way up as far as we can tell. If the Schrödinger equation always holds, all branches are real. The branch where the cat is alive and the branch where it's dead are both real. The branch where you made this choice and the branch where you made a different one are both real. The branch where this civilization continues and the branch where it ends are both real. All of them, simultaneously, in the wave function of the universe. This is the most terrifying solution to Schrödinger's cat, not because it's violent or dangerous, but because it's disorienting in the deepest possible way. It tells us that the uniqueness we feel, the sense that this moment, this experience, this timeline is the one, is a local feature, a feature of this branch. Real within this branch, but not global, not fundamental, not the whole story. The whole story is the wave function. And the wave function contains everything, all of it. Now, here's what I want to leave you with. Not a resolution, because there isn't one. Not a comfortable landing, because the physics doesn't offer one, but something true. The many worlds interpretation, if correct, doesn't diminish this moment. It doesn't make your experience less real, your choices less significant, your relationships less meaningful. It contextualizes them, places them within a structure so vast that our ordinary concepts of real and happening and now become inadequate. But inadequate concepts are not false concepts. They're concepts that work within their domain of applicability, just as Newtonian mechanics works within its domain, just as our experience of a single timeline works within the domain of everyday life. Within this branch, this moment, this experience, the ordinary concepts apply. They work. They're true enough. The quantum reality underneath the branching wave function, the simultaneous timelines, is not in conflict with the everyday reality. It's its foundation. The everyday reality is what the quantum reality looks like from inside one branch. The certainty of this moment, this choice, this experience. It's real. It's just one instance of a vast reality that is far more than any single branch can contain. The cat in Schrödinger's box is alive in one branch and dead in another. You, reading these words, are reading them in this branch and not reading them in others. All of this is happening. All of it is real. And within each branch, within each version of the story, the experience is complete, whole, genuine. You are one branch of an unimaginably vast structure. You are the part of the universe that is right now having this experience, thinking these thoughts, wondering about the wave function and the cat and the branching timelines. Other branches of you are wondering about other things, or not wondering at all. All of those branches are real. But this one, this branch, this moment, this experience, this is yours. And that, in the end, is not nothing. That is, in fact, everything.